Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is class 9, and we continue our journey through thermodynamics. Last time, the first law taught us a beautiful truth. Energy can never be created or destroyed. But sit with this for a moment. The first law tells us energy is conserved, yet it never once tells us which way a change will actually go. Ice left on a warm table melts every single time. But a puddle of water never gathers itself back into ice on its own. Both directions conserve energy perfectly. So what decides the direction? When Sarah first met this puzzle, she said, if energy is the same either way, why does nature choose one path? That is exactly the question of today's class. We meet entropy, and we meet Gibbs free energy, the true compass that tells us which way a reaction will go. And in JEE, this compass grows into some of the sharpest multi-step numericals on the paper. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the second and third laws of thermodynamics and the idea at their heart, entropy, the arrow of change. Second, spontaneity, the deep rule that the entropy of the universe always increases and how that decides which way things go. Third, Gibbs free energy, the single quantity that combines heat and disorder, written as delta G equals delta H minus T delta S. Fourth, how delta G connects to equilibrium. Delta G standard equals minus RT natural log of K and the crossover temperature, where a reaction flips between stuck and spontaneous. And fifth, the G drills, assertion and reason, match the column and the numericals. So everything you learn today, you can also score with. Ready? One idea at a time. Let us begin with the idea that governs everything today. First, entropy, written with the letter S. Entropy is simply a measure of disorder, of how many ways the particles of a system can be arranged. A tidy, ordered arrangement has low entropy. A scattered, spread out one has high entropy. Nature, left alone, drifts toward the scattered. Second, the second law of thermodynamics. In any spontaneous change, the entropy of the universe always increases. This is the arrow of time itself. Disorder, taken as a whole, only ever grows. And here is the G-level sharpening David needed. For a truly reversible process, the entropy of the universe does not merely increase, it stays exactly zero. The moment it becomes positive, you know the process was irreversible. That single distinction has decided more than one G question. Third, the third law. A perfect crystal at absolute zero has exactly zero entropy. When every particle sits frozen and perfectly ordered, disorder vanishes completely. This gives us an absolute 0 point from which all entropies are measured. And fourth, feel the pattern. As a solid melts to a liquid and a liquid boils to a gas, the particles spread out and entropy rises at every step. A gas is the most disordered state of all. When David watched steam rising from his cup, he was watching entropy climb. Now look carefully at this compass, because it is the master decision maker of the whole chapter. Enthalpy change, delta H, and entropy change, delta H, each carry a sign, and together they point to one of four boxes. First box, delta H negative and delta S positive. Energy is released and disorder increases. Both drives pull the same way, so the reaction is always spontaneous at every temperature. Delta G stays negative no matter what D you choose. This is the happiest case. Second box, the opposite corner, delta H positive and delta S negative. Energy is absorbed and disorder falls. Both drives fight the reaction, so it is never spontaneous at any temperature. Delta G stays positive always. Nature simply refuses. Third box, delta H negative and delta S negative. Energy is released, good, but disorder falls, bad. The two drives disagree. Here the reaction is spontaneous only when the temperature is low, so that the small t delta term cannot overpower the favorable delta H. We call this enthalpy driven, and this is exactly the case our worked example will use. And fourth box, delta H positive and delta S positive. Energy is absorbed, bad, but disorder rises. Good. Again, the dries disagree. This one is spontaneous only when the temperature is high, so that the large T delta S term finally wins. We call this entropy driven. Look at the whole compass once. Every reaction G can hand you lives in one of these 4 boxes. Now we take those 2 competing drives, energy and disorder, and fold them into a single honest number. First, Gibbs free energy. Its change, delta G, equals delta H minus T delta S. Look at what it does. It takes the energy released, delta H, and subtracts the temperature times the disorder gained, T delta H. One number that already knows the answer to which way better than either drive alone. Second, and this is the golden rule of the chapter, when delta G is negative, the reaction is spontaneous. It is feasible. It goes forward on its own with no outside push. Third, when delta G is exactly 0, the reaction sits at equilibrium. The forward and backward tendencies are perfectly balanced, and nothing net happens. Hold on to this line. Delta G equals 0 at equilibrium. G asks it again and again. And fourth, when delta G is positive, the forward reaction is non-spontaneous, and the reverse reaction is favored instead. Lisa used to memorize these 3 signs as a traffic light. Negative is go, 0 is wait, positive is stop. And remember, delta G standard is the same signpost pointing straight at the equilibrium constant K. Time to solve a full G numerical together. Slowly, the monk's way, and this time repeat the other sign case, the enthalpy-driven one. Take carbon monoxide reacting with hydrogen to form methanol. Its delta H is about minus 88 kilojoules and its delta Cis is about minus 220 joules per Kelvin. Below what temperature does this reaction stay spontaneous? Step 1. Read the signs. Delta H is negative. Delta H is negative. Both negative means, from our compass, spontaneous only when the temperature is low. So there must be a temperature where it just flips. Step 2. Find that flip. At the exact crossover, the reaction is balanced, so delta G equals 0. Set delta H minus T delta S equal to 0 and rearrange. The temperature equals delta H divided by delta S. Remember this little formula. T equals delta H over delta S. It works whichever sign case you are given. Step 3. And here is the trap that catches half the students. Match the units. Delta H is in kilojoules. Delta S is in joules. Convert delta H minus 88 kilojoules is minus 88,000 joules. Now both are in joules. Step 4. Divide minus 88,000 divided by minus 220. A negative divided by a negative is 400. So the crossover temperature is 400 Kelvin. Step 5. Read the answer aloud. Below 400 Kelvin, delta G is negative and the reaction is spontaneous. Above it, delta G turns positive and the forward reaction stalls. This is exactly why this kind of synthesis needs the temperature kept low and pressure raised instead to stay favorable. The same 5 steps solve every crossover problem G can ask, whichever corner of the compass it hands you. Now let us see this crossover with our own eyes on a simple graph. Delta G runs up the vertical axis, temperature runs across the bottom. First, the line itself. Since delta G equals delta H minus T delta S and delta H and delta S are roughly constant, delta G is just a straight line in temperature. One clean, straight line. That is the whole graph. Second, read its shape. Where the line meets the axis at 0 temperature, its height is delta H. That is the intercept. And here it sits below 0 because delta H is negative. Its slope is minus delta S. Here delta S is negative, so minus delta S is positive. And the line climbs upward as temperature rises. Notice this is the mirror image of the entropy-driven case where the line falls. Third, find the crucial point where the line crosses 0. At that exact spot, delta G equals 0, and that temperature is the crossover. Delta H divided by delta S, the same 400 Kelvin we just calculated, now standing before us as a single point on the line. And fourth, read the 2 regions. Below the crossover, delta G is negative and the reaction is spontaneous. Above it, delta G has turned positive and the forward reaction stalls. John finally understood the whole chapter the day he saw this line climb from negative to positive, the exact mirror image of a line that would fall. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. Spontaneous means delta G is negative, delta G is 0 at equilibrium, and delta G positive is non-spontaneous. Memorize these 3 cold. They should come to you faster than your own name. 2. The crossover temperature is delta H divided by delta Se, and always convert delta H and delta Se energy unit before you divide. That one habit saves more marks than any other. 3. At equilibrium, delta G standard equals minus RT natural log of K, with R equal to 8.314 joules per mole Kelvin. Whenever K is greater than 1, delta G standard is forced negative, and G loves building an entire numerical on exactly this line. 4. Spontaneity is about feasibility, not speed. A reaction can have a negative delta G and still crawl along slowly. Rusting is the classic example. Never confuse spontaneous with fast. 5. The entropy of the universe is the entropy of the system plus the entropy of the surroundings, and for any spontaneous change, that total is strictly greater than 0. It equals exactly 0 only for reversible change. Whenever the system loses order, check the surroundings, they may have gained even more. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. A reaction with delta H negative and delta S positive is spontaneous at all temperatures. Reason, for such a reaction, delta G is negative whatever the value of T. Think like SADA. Check each on its own, then the connection. The assertion is true, straight from our first box. Is the reason true? Yes, delta H minus T delta S is negative minus A positive, always negative. And does the reason explain the assertion? Perfectly. Both true. Reason explains. Option A. Second one, assertion. If the equilibrium constant K is greater than 1, delta G standard must be negative. Reason. Delta G standard equals minus RT natural log of K, and the natural log of a number greater than 1 is always positive. Check the reason first. Completely true. Straight from the formula. Now the assertion. If N and K is positive, then minus RT times a positive number is negative. So delta G standard is indeed forced negative. Both true, and the reason explains the assertion perfectly. Option A again. Third one, assertion. The melting of ice is non-spontaneous above 0 degrees Celsius. Reason. Melting is accompanied by an increase in entropy. Check the reason first. Melting spreads the particles out, so entropy does increase. True. Now, the assertion. Above 0 degrees Celsius, ice melts on its own, so melting is spontaneous, not non-spontaneous. The assertion is false. The reason is true. Option D. A quick match now. Say each answer aloud before I reveal it. Delta G less than 0, spontaneous. The reaction goes forward on its own. Delta G equal to 0, equilibrium. Forward and backward, perfectly balanced. Delta H negative with delta S positive, spontaneous at all temperatures. Both G's pulling the same way. And delta G standard equals minus RT natural log of K. Whenever K is greater than 1, delta G standard is negative. If all 4 came to you before the reveal, the compass is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The entropy of the universe increases in every spontaneous process. Hold your verdict. Statement 2. A reaction with a positive delta G is spontaneous. Think carefully before you answer. Statement 3. delta G standard is negative whenever the equilibrium constant K is greater than 1. So, how many are correct? Two statements, the first and the third. The entropy of the universe truly does rise in every spontaneous change, and a K greater than 1 truly does force delta G standard negative to the log term. But the second one falls. A positive delta G means non-spontaneous, the very opposite of what it claims. Two correct statements 1 and 3. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. A spontaneous reaction is always a fast reaction. It feels so natural. If it happens on its own, surely it happens quickly. David believed this for months. But here is the truth. Spontaneity means only that delta G is negative. Feasibility, never speed. Iron rusting is perfectly spontaneous, yet it takes years. Thermodynamics tells you whether, not how fast. Myth 2. An endothermic reaction can never be spontaneous. Nomas, it seems obvious. If it must absorb energy, how could it ever go on its own? The truth, if delta S is large and positive, then at a high enough temperature, the T delta S term overpowers the positive delta A and delta G turns negative. The reaction becomes entropy-driven and spontaneous. Now melting ice above zero and limestone decomposing in a kiln are both endothermic yet spontaneous. Time to test yourself, rapid fire, and today it leans heavily on numbers. Here is the rule. I ask, you answer in your head before the reveal and spell the number to yourself. No pen, no paper, just the compass you built today. Question 1. Delta H is minus 100 kilojoules and delta S is minus 200 joules per Kelvin at 300 Kelvin. What is delta G? T delta S is 300 times minus 200, that is minus 60,000 joules or minus 60 kilojoules. So delta G is minus 100 minus 60 minus 40 kilojoules. Question 2. Delta H is plus 66 kilojoules and delta S is plus 220 joules per Kelvin. What is the crossover temperature? 66,000 divided by 220, 300 Kelvin. Question 3. The G delta 1. If K equals 100 at 300 Kelvin, what is delta G standard? Using minus RT natural log of K with R equal to 8.314. That works out to about minus 11.5 kilojoules. Question 4. What is the sign of delta G at equilibrium? It is 0. And question 5. If delta H is negative and delta S is negative, at which temperatures is the reaction spontaneous? Only at low temperature. If you caught all 5, you have truly understood today's class. Let us gather the whole class in one slow breath. Entropy is disorder, and the entropy of the universe always increases in a spontaneous change. That is the second law, the arrow of all change. Gibbs free energy ties the two drives together. Delta G equals delta H minus T delta S. Delta G negative is spontaneous, delta G is 0 at equilibrium, and delta G positive is non-spontaneous, the traffic light of chemistry. The 4 sign cases decide feasibility, and the crossover, where a reaction just flips, is the temperature delta H divided by delta S. At equilibrium, delta G standard equals minus RT natural log of K. And remember, spontaneity is feasibility, not speed. And next class, we walk into chemical equilibrium itself. The equilibrium constants, Kc and Kp, the reaction quotient, and Le Chatelier's principle. Do not miss it. And so, my friend, we have found the compass. It may have looked like just one line. Delta G equals delta H minus T delta S. But understand this. That single line decides the direction of every reaction in all of chemistry. Whether a reaction will go, whether it has reached equilibrium, whether cooling or heating will finally set it free, all of it is written in the sign of delta G, and now you can compute the exact crossover T for either sign case G hands you. Sarah, David, Lisa, and John all sat exactly where you are now, and this is the class where direction finally made sense to them. Be patient with yourself. Tonight, revise the 4 sign cases once, slowly, and picture that line crossing 0, both climbing and falling. One idea at a time, you will crack JEE. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you at equilibrium.